Hello students. In this lesson, we are going to study about the second part of photochemical reactions of transition metals complexes. In content, we will cover the following topic: Photo-redox reactions, Ligand photoreactions, and Photoreaction and solar energy conversion. Photo-redox reactions. In general, the electronic transitions promote photo-redox reactions, which are charge transfer transitions. These transitions primarily change the radial distribution of the electron involved relative to the metal nucleus, in contrast to the angular rearrangement that occurs in dd transitions. If the electron originates in a molecular orbital that is essentially ligand-based, and moves to a metal-based molecular orbital, the metal has been reduced, and the ligand has been oxidized. Such a transition is called either ligand-to-metal charge transfer, LMCT, or charge transfer to metal, CTTM. On the other hand, if the electron moves from a metal-based molecular orbital to a ligand-based molecular orbital, the transition is a metal-to-ligand charge transfer, MLCT, or charge transfer to ligand, CCTL, transition. Cobalt-3+ complexes characteristically undergo LMCT transitions to yield label cobalt-2+ complexes, so that substitution accompanies the photo-redox reaction. One interesting complex that undergoes CT photoactivation is the bipyridyl complex of ruthenium 2 and tri-bipyridine ruthenium 2. This D6 complex can also exist with the same stoichiometry as a 1-, 0, 1+, and 3+ species. It thus has a rich redox chemistry, and many opportunities for CT transitions. This figure shows the structure of the complex, and gives a modified Latimer diagram for the three principal ruthenium oxidation states. The bottom line is the sequence of conventional reduction potentials. The species tri-bipyridine ruthenium 2 at the top is the excited state, resulting from an MLCT transition that absorbs a frequency corresponding to an excitation energy of 2.1 electron volt. This lowers the 3+/2+ potential by 2.1 volt, and raises the 2+*I and potential by 2.1 volt. That is, the excited use is both a better oxidant and a better reductant. So, although the 2+ complex is stable with respect to disproportionation in water, the 2+ excited state, spontaneously disproportionate to the strong oxidant, 3+ species, and the strong reductant, 1+ species. An interesting sidelight is that the 3+ species in aqueous solution can be reduced by hydrazine, or a hydrated electron, to give the 2+ excited state chemically. This is a triplet state that phosphoresces orange light on returning to the 2+ ground state. Since the excited state was produced chemically, rather than by radiation absorption, the phosphorescence is called chemiluminescence. Ligand photoreactions. Ligand photoreactions tend to arise from transitions between ligand-centered molecular orbitals. This implies that the metal-to-ligand bonding is changed little, or not at all, by the ligand reaction. This is certainly true for reactions such as the isomerization, as shown in the reaction. Here, the tungsten hexacarbonyl is photo-assisting the stilbene, since it will photo-isomerize without metal coordination. However, the 40% trans and 60% cis mixture is produced, regardless of which isomer of stilbene is used as the reactant. Many other alkenes undergo similar isomerization as monometallic ligands, usually more readily for terminal double bonds than for internal ones. Some ligand photoreactions clearly do change the nature of the ligand to metal bonding. An unusual pi to sigma shift occurs for the ligands 1,2-dicyanoacetylene and tetracyanoethylene. These are formally similar to insertion reactions. However, D6 systems are particularly stable in square planar complexes, where they have a total of 16 valence shell electrons, as you can see here. So, for the platinum 2D8 product of the above reactions, a comparable insertion reactive species might be a 2-coordinate 14 electron complex. This corresponds to bis triphenylphosphine, platinum, an intermediate that might form if the photoreaction simply dissociated the pi ligand. Other ligand photoreactions involve free potential ligand molecules that appear to combine with transition metal photocatalysts, react, and dissociate, either as an excited state that forms the product, or as the product itself. Butadiene is hydrogenated by H2 when irradiated in the presence of chromium hexacarbonyl to give butene. Now, we will discuss its mechanism. The mechanism for this reaction probably involves repeated photodissociation of carbon monoxide, followed by diene coordination and H2 coordination. See figure, as shown here. The photodissociation of chromium hexacarbonyl has been extensively studied, and the original excitation and dissociation to chromium pentacarbonyl yields a molecule that is sufficiently vibrationally excited to dissociate a second CO rapidly. The chromium tetracarbonyl product of this dissociation is stable toward further dissociation, but can accept 2 more pairs of electrons, as shown in the figure, to give the product. Photoreaction and solar energy conversion. There are 4 photochemical processes for solar energy conversion, using the photoexcitation of redox couples in water. Number 1, a semiconductor solution junction, with a redox couple, yielding no net chemical change. Number 2, a semiconductor solution junction, with water decomposition, using photo-assisted electrolysis. Number 3, a semiconductor solution junction, with water decomposition, using high-frequency radiation. And the last one is a solution species, yielding a strong oxidant and reductant on irradiation. Here, we will discuss the 4 photochemical process, one by one. A semiconductor solution junction, with a redox couple, yielding no net chemical change. If the semiconductor solution junction is irradiated, to excite a valence band electron to the conduction band, it will relax by moving towards or away from the junction, depending on the direction of bending. In case 1, as shown in figure A, if the excited electron relaxes down into the redox couple in solution, the couple is then reduced, and the junction behaves as a photocathode. In case 2, as shown in figure B, if the electron relaxes by moving away from the junction, and the hole moves toward the junction, stripping electrons from the redox couple in solution, and oxidizing it. Here, the junction serves as a photoanode. In either case, a counter-electrode must be supplied in the solution to allow electron removal or return, serving the same function as the back contact on the silicon solar cell. If a reversible redox couple is chosen, then oxidation at one electrode will be just balanced by reduction at the other electrode, and no net chemical reaction will occur. A semiconductor solution junction with water decomposition using photo-assisted electrolysis. If we eliminate the reversible redox couple from the solution, the solvent itself, water, can serve as the redox couple. H2O will be reduced to H2 at the semiconductor electrode if the semiconductor is a p-type photocathode, and will be oxidized to O2 at the counter electrode. A good example of this sort of cell uses p-type indium phosphide as the photoelectrode, HCl-KCl solution as the electrolyte, and platinum as a counter electrode. However, the band gap for indium phosphide is small enough that the light energy, HV, is not great enough to force the reduction and oxidation of water. Instead, a voltage is maintained across the two electrodes externally. The water is simply electrolyzed, but instead of requiring 1.21 volt for decomposition, the cell with the photocathode, irradiated by sunlight, requires only 0.64 watt, so that much less external electrical energy is consumed. A semiconductor solution junction with water decomposition using high-frequency radiation. The semiconductor solution system for the photolysis of water to H2 and O2 is to choose a semiconductor for which the band gap is so large that the light absorbed yields enough energy to split water without any added external voltage. For such a system, water would be reduced by the very high energy conduction band electron at an anionic site on the semiconductor surface, while a hole in the low energy valence band would oxidize water at a positively charged site. The semiconductors, titanium dioxide, which is N-type, and gallium phosphide, which is P-type, combined in a single particle, have this ability. So does N-type strontium titanate, partially coated with platinum metal. Here, oxidation occurs at the N-type surface, and reduction at the P-type, or metal surface. The major drawback of these systems is that the high energy radiation required, the uses of only ultraviolet portion of the sun's radiant energy, which is only a small fraction of the total energy input at the Earth's surface. A solution species yielding a strong oxidant and reductant on irradiation. An alternate possibility for separating the oxidation and reduction sites is to use a semiconductor solid as a relay compound. If the photosensitive compound is adsorbed on the surface of a small particle of solid semiconductor suspended in solution, it can release an electron from its photoexcited state into the semiconductor, which can release the electron to H2O at another surface location. In this case, the solid particle can also serve as the support for the required catalysts. Semiconducting titanium dioxide particles have been successfully used as the support for platinum and ruthenium oxide in the system, with free H2 and O2 generated directly by irradiating the aqueous suspension. Converting tri-bipyridine ruthenium 2 to an anion by using as a ligand 2,2-bipyridyl 4,4 decarboxylate greatly improves the electrical interaction of the photosensitive ruthenium species with the titanium dioxide semiconductor. Such a system has yielded 44% photon to current efficiency for a given frequency of irradiation. Thank you.